Okay, so we're going to go ahead and start working on evaluating these and using mental math, but I need to kind of show you, like a prerequisite. So let's say we have these two numbers, a 2 and a 32, and I want you to rewrite them using the same base. So sometimes you're going to have to change both numbers. Sometimes you're going to only be able to change one of them. So when I'm looking at the 2 and the 32, I'm thinking, okay, well, how can I rewrite a 32 with a base of 2? You always want to go to a smaller base. I can't change a 2 into a 32. The 2 is going to have to stay as 2, and now the 32 is going to become 2 to the 5th power. So this is 2 to the 1st power, and then 2 to the 5th power. They both have that same base of 2. So sometimes, like in this case, we only change the 32 to become a 2. Now when we look at 25 and 125, we're going to have to say, okay, what base can they be that's going to make them both the same base with different exponents. So hopefully you see that 25 and 125 both have that base of 5 in common. So 25 would be 5 squared, and 125 would be 5 to the 3rd power. So now they're written as the same base of 5. Notice that we changed the 25 and the 125 into a smaller number. We didn't try to make them into a larger number. Now, when I say smaller number, I am kind of disincluding fractions because I want to try to have non-fraction bases only because I think we're more comfortable with not having fractions. So when I look at the 1/4 and the 8, what I'm going to do is I'm going to change this. I'm going to change this to 4 to the negative first and 8. And then I'm going to think about changing those bases, the 4 and the 8, to be the same. And I'm going to think, okay, well, 4 is really 2 squared. And now we have that to the negative first. And 8 is 2 to the 3rd. So hopefully you remember properties of exponents tells me I'm just multiplying my powers to a power. So my final answer would be 2 to the negative second and 2 to the 3rd. And hopefully you see 2 to the negative second really is 1/4 and 2 to the 3rd is 8. But now again, we have those same bases. So when we want to evaluate expressions by using mental math, we're going to want to change the sides to have the same base. So the first thing you're going to do is you're going to set it equal to x. So we're going to do something that I always tell you not to do. I say you don't have the power to put an equal sign in the problem, but now I'm granting you those special powers. Congratulations. Then you're going to change it and you're going to write it in exponential form. So this is what we just did. Where we practice, we have that same base, and then we're switching the sides. Then you change each side to have the same base. You're always changing to a smaller number. That's kind of what I just showed you. And then you evaluate. Then you solve. You equate your exponents essentially here. That's what this means. Equate exponents. And I'll show you exactly what I mean. So the first thing we're going to do, we're going to take log base 5 is 25, and we're going to set that equal to x, just like our directions say. Then we're going to go ahead and change the form. So the base is 5, which means the exponential base is going to be 5, and then these two things are going to switch places. So now the exponent is x, and that's going to equal 25. So now I know you probably can figure out that 5 to the 2nd power is 25, and you can realize that x equals 2, but let's practice here, trying to make the 5 and the 25 into the same base. So I'm going to leave that 5 to the x, and I'm going to change that 25 to 5 to the 2nd power. Once we have the same bases, you can go ahead and set your exponents equal to each other. Sometimes you're going to have to solve. In this case, we say x equals 2, and we're done. We don't have to solve for x. So looking at this next one, log base 9 of 27. So the first thing I'll do is I'll set that equal to x, then I'll change the form. Log base 9, so now I'll have exponential base 9, and these two values will switch places. So the exponent is going to be x now, and that's going to equal 27. So now I'm trying to turn a 9 and a 27 into the same base. Can I make 27 into 9? No. But I can make 9 and 27 into a smaller number of 3. So I can change 9 into 3 squared, and we still have that x. And I can change 27 into 3 to the 3rd. Well, now that we have the same bases, I can go ahead and set my exponents equal to each other. So I'll have 2x equals 3, divide by 2, and I'm going to see x equals 3 halves. That got a little squished there, sorry. So 9 to the 3 halves equals 27. Think about that. Think about doing that problem. 9 to the 3 halves equals 27. 9 to the 3 halves equals 27. Remember changing that radical, so the square root of 9 cubed equals 27. This is a true statement. This is all hopefully coming together for you. Now this last problem, we go ahead and we set this equal to x, and then we have to remember our special logs. So we don't see a base written there. We have to remember that there's really a little teeny tiny 10 there. So this is going to become 10 to the x equals 1,000. So I'm going to try to change 10 and 1,000 to have matching bases. So my 10 is going to be the x power, and 1,000 is going to become 10 to the third power. Then I can go ahead and set my exponents equal to each other because I have the same base. That's your go ahead to do that. So we'll see x equals 3, and we're done. And by done, I meant with that problem. You know, we're never really done here in Papa 2. So go ahead and set that equal to x, change the form. So log base 4 means exponent base 4, and then my exponent is x equals 1/8. So now I'm looking at the 4 and I'm looking at the 1/8, and I'm trying to make them have the same base. Hopefully you see we're going to use 2. So I'm going to change 4 into 2 squared, and we still have that exponent of x. And I'm going to change 8 into 2 to the negative third power. So when you change a fraction base into a whole number base, your exponent's going to have to be negative because we're really flipping that. Now that I have those matching bases, I can go ahead and set my exponents equal to each other. So I'm going to have 2x equals negative 3, divide by 2, so x equals negative 3/2. Now, if we think logically about this problem, in order to get 4 to some power to equal a fraction, hopefully you're realizing that that answer is going to have to be negative because anything to a negative exponent is going to flip that to become a fraction. This next one here, natural log of e. So natural log of e, set that equal to x. Remember that natural log is really base e. So this is really a little tiny e there. So it's really like log base e of e. Now I want you to really think that this is a special inverse property. Okay, so we've got this log base e of e equals x. Since these are matching, we should hopefully understand that that's going to become 1. But we can go ahead and change this to exponential form. This is my base e here, so that's going to be my exponential base. And then these two pieces are switching places. So e to the x equals e. Well, remember that e really has an imaginary 1 there. So since they have that same base, we can go ahead and equate our exponents and say that x equals 1. If you recognize that at this point, you don't have to show that other step. Hopefully, eventually, soon, once we get more familiar with this, you'll realize that natural log of e is 1 automatically. And now this last one here, we're going to say log base 7 of 1 equals x. Go ahead and change that, base 7 for your exponent also. The x becomes the exponent equals 1. So now in this case, we can't change a 7 into a 1 or a 1 into a 7. There's just no way to get that those numbers to have the same base. But what we have to remember are our properties of exponents. And anything to the 0 power is going to be 1. So this is going to tell us that x equals 0. This is another special property, and that's anytime you take the log of 1. It doesn't matter what your base is. When you take the log of 1, your answer is going to be 0, and that's coming from this right here. So now we're going to go ahead and evaluate logs. So that means we're just going to type them in our calculator. Log of 12, like I told you, your calculator will only evaluate base 10. So this log 12 is like log base 10 of 12. You're going to look for that button that says log. On the calculators like we have in class, they're right underneath that second function. You're just going to press log 12. It's a good habit to get into to close your parentheses and then press enter. We're rounding to the nearest hundredth, so that's going to be 2 decimal places. So you should get 1.08 for this first one. Now the natural log, you don't need to type in log base e of 0.75. First of all, you can't because your calculator only evaluates base 10. So natural log has its own button, and it's usually right below the log button. So it looks just as ln. So type in ln of 0.75, close your parentheses, and you should get negative 0.29. If you continue to type these in, or maybe you recognize that we have a special log property here because those are the same, so this one's going to be 1. You can't type that in your calculator because it's not a base 10. Natural log of e, you could type that in your calculator, but when you type in your calculator, you're going to get natural log. E is the second button. You'll see a little e to the x. So you'll have to type in e, and then you'll have to make that to the first power. But I want you to start to realize that those are just going to become 1. And then log base 7 of 1. Again, you can't type that in your calculator because it's a base 7, but we need to start recognizing that this is a special log property and that when you take the log of 1, it's always going to be 0.